Welcome to the 2 a.m. Theory Podcast. This is where late night thoughts turn into late night conversations.
Right now, somewhere in the universe, time is moving differently than it is for you.
Yeah, it's a staggering reality to confront, honestly.
It really is. I mean, if you are listening to this right now, maybe it's late at night, maybe the room is quiet, and all you can hear is the subtle, relentless ticking of a clock on the wall.
Right, that sound we all know.
Exactly. We build our entire lives around that uniform ticking. We just assume it's the heartbeat of the universe.
But that ticking, that is a localized, incredibly stubborn illusion.
And it's an illusion we are entirely obsessed with. Think about your day-to-day. You probably checked your phone, 100 times just to see the hour?
Oh, easily. I mean, we measure our entire worth and productivity per hour now.
We do. We stress over being late. We fear aging. Ultimately, I think we just fear the end of our time.
Which makes perfect sense from a psychological standpoint.
Right. And I think that's exactly why the concept of time travel has fascinated humanity for so long.
Yeah.
It is the ultimate escape fantasy.
Oh, absolutely. It's the ultimate what if.
Think about the movies. It's Marty McFly jumping into the DeLorean in Back to the Future. That is the pop culture entry point for almost everyone alive today.
The flux capacitor.
The flux capacitor, exactly. We love the idea that if we just drive fast enough or invent the right machine, we could escape the forward march of the clock.
We desperately want to believe we aren't trapped.
What if we aren't just moving forward? What if we could actually escape time itself?
Well, you'd think that belongs strictly in the realm of Hollywood. But surprisingly, modern physics says time travel may already exist.
Wait, really? Already?
Yes. And it doesn't require a DeLorean at all. It requires an understanding of how the universe is actually constructed.
Okay, color me intrigued.
The math, specifically originating from Albert Einstein's theories of relativity, suggests that time travel isn't just some science fiction trope.
That's what baked into the physics.
Exactly. The mechanisms might already be written into the fundamental laws of reality. We just need to know where to look and, well, what we are looking at.
So tonight, we are taking you, wherever you're listening to this right now, on a deep dive into the absolute mystery of time.
It's going to get weird.
It's going to get so weird. We're going to question whether the rigid clock you live your life by is actually just a stubborn illusion.
We're going to look at the real science here.
Real science. We're talking wormholes, black holes, paradoxes that literally break reality, and the terrifying existential possibility that your future may already exist.
It's a journey that starts with challenging our most fundamental perception of reality.
Which is hard to do.
Very hard. We basically have to completely dismantle the idea that time is a straight line moving at the exact same speed for everyone.
So how do we even begin to dismantle that? Because for the vast majority of human history, time was just, it was just time.
Right.
It was a universal metronome. The assumption was always that a second for me sitting here in this studio is exactly a second for you.
And a second for someone standing on the surface of Mars.
Right. And a second for a star exploding a billion light years away. It was just this absolute invisible backdrop to the universe.
That is the perfect way to describe the Newtonian view of the universe, actually.
Okay, Sir Isaac Newton.
Yeah. Newton essentially formalized what human common sense tells us. He pictured time and space as a rigid, unmoving stage.
Like a theater stage.
Exactly like a theater. All the events of the universe, stars forming, planets orbiting, humans living their lives, they were just the actors moving around on that stage.
But the stage itself is solid.
Right. The actors change, but the stage itself never changes. The clock of the universe ticks uniformly for everything, everywhere, forever.
Which makes intuitive sense to our monkey brains, frankly.
Of course it does, because we all move at incredibly slow speeds relative to the cosmos, and we all live in the exact same gravitational field here on Earth.
We don't have any frame of reference for anything else.
Precisely. But in 1905, a young patent clerk named Albert Einstein completely shattered that rigid stage.
With special relativity.
Yes. And then he broke it even more profoundly in 1915 with general relativity.
Okay, so what did he actually say that was so paradigm shifting?
He proposed something so radical that physicists of his day actively fought against it. He said that space and time are not separate entities.
They aren't the stage.
No, they are interwoven into a single dynamic four-dimensional fabric. We call it spacetime.
Spacetime. Okay, and if I'm understanding this correctly based on our sources, this fabric is not rigid like Newton thought. It's flexible.
Highly flexible.
It can be manipulated.
It can be warped, stretched, bent, and twisted.
That is wild. So what actually warps it?
Two things, primarily. Speed and gravity. Let's look at speed first.
Okay.
The faster you move through space, the slower you move through time relative to a stationary observer.
And that's special relativity.
Exactly. And then general relativity adds gravity to the mix. Gravity isn't just a magnet pulling things to the ground.
Right. It's not just a force pulling my coffee cup down.
No, gravity is literally the curving of space-time by mass.
So a heavier object bends the fabric more.
Yes. The closer you are to a massive object like the Earth or the Sun or a black hole, the stronger the gravitational pull and the slower time moves for you.
So time is not a universal constant at all.
Not even close. It is entirely relative to your speed and your proximity to mass.
I want to pause here because I really want the listener to grasp this. This isn't just theoretical math on a chalkboard hidden away in some university basement.
No, this is measurable reality.
Right. This is a physical reality that we can measure right now.
Right.
Let's talk about the NIST experiment from 2022. Because when I read this in our research for this deep dive, I had to put the paper down and just stare at the wall for a minute.
It's a beautifully elegant demonstration of Einstein's math, isn't it?
It really is. So NIST, the National Institute of Standards and Technology, they did something absolutely mind-blowing.
They didn't use spaceships or black holes.
No. They built 2 optical atomic clocks. And these aren't your grandfather's ticking clocks.
Definitely not.
These are unbelievably precise instruments that measure time by observing the incredibly fast, stable vibrations of atoms.
And they placed 2 of these atomic clocks in the exact same cloud of ultra-cold atoms.
Right. They were trying to measure time dilation, the stretching of time due to gravity, at a scale so incredibly minuscule that no one thought it was physically possible to detect.
Until they did it.
And they separated these 2 tiny clocks by just 1 millimeter.
1 millimeter.
1 millimeter. For anyone listening, hold up your thumb and index finger right now. Bring them so close together they're almost touching. That is the width of a sharp pencil tip.
It's microscopic in the grand scheme of things.
And because of the Earth's gravity, specifically because the clock that was 1 millimeter lower was infinitesimally closer to the center of the Earth, it actually ticked at a different rate than the clock 1 millimeter above it.
It ticks slower.
Wow.
Yeah. The gravitational field was slightly stronger at that lower elevation by a margin so small it basically defies human comprehension.
Yet that difference caused a measurable time dilation.
Yes. The lower clock experienced less time than the upper clock. It perfectly matched the predictions of general relativity.
Wait, hold up. Let me make this personal for a second. If you are telling me that a 1 millimeter difference in height changes the flow of time,
It does.
are you saying my head is literally aging at a different rate than my feet?
That is exactly what the physics dictates.
That is insane.
Think about it. Because your feet are closer to the Earth's center of mass than your head, they experience slightly stronger gravity.
So they move through time slower.
Therefore, your feet are moving slower through time. Your feet are literally younger than your head.
That is deeply unsettling. I am sitting here right now and different parts of my body are existing in different temporal reality.
By a fraction of a second so small you could never notice it over a billion lifetimes, yes.
But it's real.
But it is a physical reality. You are not moving through time uniformly. None of us are.
Okay, my brain is already melting, but let's scale this up. Because if it happens at the scale of a millimeter, it must wreak havoc on a larger scale.
Oh, it does.
We rely on aerospace engineering every day. What happens when we put machines into space?
It is a massive daily engineering hurdle. Honestly, if aerospace engineers ignored relativity, modern society would collapse.
Wait, society would collapse? How?
Take the European Space Agency's Gaia mission. Gaia is a space observatory mapping billions of stars, and its scientific measurements require microsecond accuracy.
Okay, so it needs to be incredibly precise.
Very. But Gaia is out in deep space. It's further away from the Earth's gravity well than we are, meaning time should speed up for it.
Because there's less gravity.
Exactly. But it is also moving at incredibly high speeds, which means time should slow down for it.
Due to special relativity.
Right.
So it's getting pulled in 2 different temporal directions at the same time.
Precisely. And the net result is that its onboard clock experiences significant time drift compared to the clocks sitting in the control room back on Earth.
So they get out of sync.
If the ESA engineers did not constantly run Einstein's equations to artificially correct Gaia's clocks, the data would be corrupted and the mission would fail entirely.
And this affects everyone listening right now, right? Not just astronomers. Because of GPS.
Absolutely. The GPS satellites orbiting Earth are experiencing the exact same war of relativity.
How fast are they moving?
They are moving very fast relative to the ground, about 14,000 kilometers per hour.
Okay, so that's special relativity kicking in.
Right, which slows their time down by about 7 microseconds a day. But they are also 20,000 kilometers above the Earth,
General relativity. They feel less gravity.
meaning they feel much less gravity than we do,
Oh.
which speeds their time up by about 45 microseconds a day.
So you do the math. 45 minus 7.
The net result is that a GPS satellite clock ticks faster than your phone's internal clock by about 38 microseconds every single day.
Which, honestly, 38 microseconds does not sound like a lot.
It doesn't until you realize that light travels about 300 meters in one single microsecond.
Oh.
Yeah. GPS works by measuring the exact time it takes for a light speed signal to reach your phone from the satellite.
So if the time is off even a little bit?
If we didn't mathematically correct for that 38 microsecond temporal drift, the GPS system would be off by over 10 kilometers within a single day.
10 kilometers.
In 2 days, Google Maps would tell you you're in the wrong city.
That is wild.
The entire global navigation system, global supply chains, aviation, all of it relies on the fact that time is an illusion that we have to mathematically correct for.
And it's not just human-made machines experiencing this. I remember reading about subatomic particles in the sources, muons.
Yes, muons. The universe naturally demonstrates this time bending all the time.
What exactly is a muon?
The muon is essentially a heavy cousin of the electron. When high-energy cosmic rays from deep space slam into the upper atmosphere of the Earth, they create showers of these muons.
Okay.
Now, muons are incredibly unstable. They have a known fixed lifespan. They decay and vanish into other particles in about 2.2 microseconds.
Okay, so they are born high up in the atmosphere, and they literally only live for 2 millionths of a second.
Correct.
According to classical Newtonian physics, even if they were moving at the absolute speed limit of the universe, the speed of light, they could only travel a few hundred meters before they died.
They should never reach the ground. It should be physically impossible.
But they do.
They do. We detect them constantly on the surface of the Earth. In fact, if you hold out your hand right now, a muon is passing through it about once every second.
How is that possible if they die before they can make the trip? That makes no sense.
Because they are moving at 99.9% the speed of light. And at that speed, special relativity kicks in with extreme prejudice. From our perspective, standing on Earth, looking up at them, their internal clock slows down drastically.
The time for them is crawling.
Their 2.2 microsecond lifespan is stretched out, dilated, allowing them to survive long enough to travel the 15 kilometers down to the surface.
So they live longer relative to us. But what about from the muon's perspective? Does it feel like it lived a long life?
That's the beautiful symmetry of relativity. From the muon's perspective, its clock is ticking completely normally. It lives its brief 2.2 microseconds and dies.
Wait, then how does it reach the ground from its own point of view?
Because it is moving so fast, space itself contracts.
Brace, contract.
The 15-kilometer distance from the upper atmosphere to the ground literally shrinks to a few hundred meters from the muon's perspective.
That is breaking my brain.
For the muon, time is normal, but space is squished. For us, space is normal, but the muon's time is stretched. Both perspectives are equally valid.
Okay, so speed alters time. Gravity alters time. My feet are younger than my head, and particles are surviving their own deaths because of speed.
You got it.
Let's take this to its logical, terrifying conclusion. If we can dilate time by fractions of a microsecond using modern technology, what happens if we push the universe to its absolute limit?
Things get very interesting.
If I want to travel into the future by years or decades, how do I actually do it?
You accelerate. If you have enough energy, travel into the far future isn't just a theoretical possibility. It is a guaranteed, unavoidable consequence of relativity.
And there's a famous thought experiment for this, right?
Yes. The most famous illustration of this, and physicists have debated the implications of this for a century, is the twin paradox.
I love the twin paradox. Let's break this down for the listener. Imagine you, the listener, have a twin. Let's call them Romulus and Remus.
Good classical names.
Right. Romulus decides to stay here on Earth, living a normal, everyday life, paying taxes, mowing the lawn.
Safe and stationary.
Exactly. Remus, however, gets recruited for a deep space mission. He gets into a highly advanced spacecraft and travels to the nearest star system Alpha Centauri, which is roughly 4 light years away.
And Remus is traveling incredibly fast, let's say 80% or 90% of the speed of light.
Okay, so he's really moving.
When Remus completes his journey to Alpha Centauri, turns around, and flies back to Earth at that same speed, the reunion is going to be deeply traumatic.
Traumatic how?
Remus might step off the ship feeling like he has only been gone for, say, 5 years. His biological clock, his ship's clocks, his memories, they all align with 5 years of lived experience.
Okay.
But when he looks for his twin, he will find that Romulus has aged 20, maybe 30 years.
Wow.
Remus has effectively used velocity to travel decades into Romulus's future.
But wait, I need to play devil's advocate here because this is where my brain always trips up on relativity.
Go for it.
You just said earlier that from the muon's perspective, space contracted. Relativity says that motion is relative.
It does.
So if I'm Remus, sitting inside my spaceship drinking coffee, I feel completely stationary. If I look out the window, it looks like the Earth is hurtling away from me at 90% the speed of light.
That is an accurate observation from his perspective.
So shouldn't Remus think Romulus is the one moving fast, and therefore Romulus should be the one aging slower? If motion is relative, why is it definitively Remus who comes back younger? Why isn't it a tie?
You have just articulated the exact reason it is called a paradox. It seems like a logical contradiction. Why does Remus win the youth lottery?
Exactly. Why him?
The resolution lies in a concept called inertial reference frames, and understanding why the symmetry between the twins is broken.
Break that down for me. What is an inertial reference frame?
An inertial reference frame is simply a state of moving at a constant velocity without accelerating or decelerating. Coasting, essentially.
Okay.
So special relativity's weird rule that each observer sees the other aging slower strictly and only applies if both observers stay in their own constant, unaccelerating inertial frames forever.
But Remus doesn't do that.
No. Remus's journey isn't constant. He doesn't just coast forever.
Right. To go to Alpha Centauri and come back, Remus has to step on the gas. He has to accelerate up to near light speed, cruise, slam on the brakes to turn around to the star, hit the gas again to come home, and then decelerate to land.
Exactly. Romulus, sitting on Earth, basically stays in one inertial frame the entire time. He never feels the crushing G-force of acceleration.
He's just hanging out.
Remus, however, actively switches reference frames. When Remus reaches Alpha Centauri and fires his engines to turn around, he physically shifts from an outbound reference frame into an inbound reference frame.
And what happens during that shift? That's the crucial part, right?
It is. During the outbound trip, Remus looks back at Earth and calculates that Romulus's clock is running slow.
Okay.
But during the intense acceleration of turning around, Remus is shifting through infinite reference frames. If he calculates what time it is on Earth during that turnaround, Romulus's clock appears to violently fast forward.
Just absolutely blurs forward.
By the time Remus settles into his inbound cruising speed, Romulus's clock has jumped far ahead. It's the physical act of accelerating, changing direction, and shifting frames that breaks the symmetry. The universe knows who actually accelerated.
That is fascinating. The universe keeps the receipt for the acceleration.
That's a great way to put it.
This reminds me so much of Christopher Nolan's movie Interstellar.
Oh, perfect example.
That movie is essentially a masterclass in making the physics of relativity terrifying for a general audience.
It really is.
There is that famous scene where they land on Miller's planet, which is covered in shallow water. And the defining feature of this planet is that it is orbiting incredibly close to a supermassive black hole named Gargantua.
1 hour here is 7 years on Earth.
Yes, that line. They know they only have a few hours to grab the data and get out because every single second they waste, their families back home are aging and dying.
The tension is incredible.
And when they finally get back to their main ship, their crewmate, who stayed behind, has gray hair and has been waiting for 23 years. That's not just Hollywood drama, right? That is scientifically accurate.
It is remarkably accurate. In fact, Kip Thorne, the Nobel laureate physicist, was the science advisor and executive producer on Interstellar.
Really? A Nobel laureate?
Yes. He calculated the exact spin and mass Gargantua would need to produce that specific time dilation for Miller's planet. Which brings us to the second way to time travel. We talked about speed with Remus. Now we need to talk about gravity. Because Miller's planet wasn't moving at light speed, it was just deep in a gravity well.
Okay, so speed alters time. Gravity alters time. I want to try to visualize how gravity actually messes with the future. because it's hard to picture. Let's talk about light cones. I love this visual from the research.
A light cone is a foundational concept in physics for visualizing causality, cause and effect.
Okay, paint a picture for us.
Imagine you, the listener, are standing in a dark, empty void. You are a single point in space and time. Now imagine a cone shape expanding upward and outward from your body.
Like an upside-down ice cream cone above me.
Exactly. That cone represents your future. It defines every possible location in the universe you could ever reach and every event you could ever influence.
Why is it limited by a cone shape, though? Why not just an infinite sphere?
Because the absolute speed limit of the universe is the speed of light. The edges of that cone represent a beam of light shooting out from you. Since you cannot travel faster than light, your entire possible future, every choice you make, everywhere you go, must physically exist within the boundaries of that expanding upward cone.
So anything outside the cone is just what? Off limits?
Anything outside the cone is causally disconnected from you. You can never reach it, and it can never affect you.
And in flat, empty space, far away from any planets or stars, that cone points straight up, straight forward into the future.
Yes. The march of time is perfectly vertical.
But as Einstein taught us, mass warps space-time.
Right. Gravity isn't just a pull, it's a bending of the geometry of the universe. When you get near a massive object like a super-dense neutron star or a black hole, the space-time is so warped that your light cone actually tilts toward the object.
Wait, it kills.
The gravitational pull is literally dragging your possible futures toward it.
I want to make sure I'm picturing this right. If I am in a spaceship hovering near a black hole, my light cone is tilted inward toward the darkness, which means my future is literally pointed at the black hole.
Precisely.
That is terrifying.
If you cross the event horizon of a black hole, space-time is so extremely warped that your light cone tilts entirely inward.
Meaning what?
Every single path forward in time leads to the center of the black hole, the singularity. It is no longer just a place in space. It becomes your inevitable future.
Wow.
You can no more avoid moving toward the singularity than you can avoid moving toward tomorrow.
That is horrifying. But it leads to a mind-bending question. If gravity can tilt the direction of my future, how far can it tilt?
Here is where the math of general relativity gets truly bizarre, and where the possibility of going backward in time emerges.
Backward, now we're talking.
If the curvature of spacetime is extreme enough, the math suggests that a light cone doesn't just tilt sideways. It can tilt beyond 45 degrees.
Okay.
It can tilt so far over that it lies completely on its side, or even points downward.
Downward, meaning into the path.
Yes, it tilts your future into the past.
What does that even look like?
The path through spacetime loops completely back on itself. If you travel forward along your timeline, moving into your own future, you could eventually intersect with your own external past.
It's a loop. It's an actual physical loop in the fabric of reality.
In physics, we call this a closed time-like curve, or a CTC.
Closed time-like curve.
It is exactly what it sounds like. It is a trajectory through space-time that perfectly obeys the speed limit of light. You never go faster than light, so it's time-like. But the geometry of space is so twisted that moving forward brings you back to the exact time and place where you started.
It is the mathematical definition of a time machine.
Yes, it is.
Which brings me to one of my favorite movies of all time.
Yeah.
Contact, based on the novel by Carl Sagan.
A classic.
For those who haven't seen it, Jodie Foster plays a brilliant radio astronomer who finds a signal from an alien intelligence. The aliens send blueprints for a massive, terrifying machine.
Right, the ring.
Foster's character gets strapped into this pod, and she is dropped through these giant spinning rings. From the perspective of mission control on Earth, the capsule just drops straight through the rings and splashes into the safety net below.
A fraction of a second passes.
Yeah, it looks like a total failure to everyone watching.
But for her,
inside the machine, everything changes. She travels through this kaleidoscopic wormhole, visits a beach in another star system, has a deeply emotional conversation with an alien taking the form of her dead father, and experiences 18 hours of time.
an incredible sequence.
When she gets back and tries to prove it to the government, they think she's crazy because only a second passed. Until they realize her video camera recorded 18 hours of pure static.
The ultimate proof.
Now, the crazy thing is, Carl Sagan didn't just pull that out of his imagination, did he?
No, he didn't. Sagan was a brilliant astrophysicist, but he wanted his science fiction to be as rigorous as possible.
So he asked for help.
When he was writing the manuscript for Contact in the 1980s, he specifically reached out to his friend, Kip Thorne.
The same Kip Thorne, who would later work on Interstellar.
The very same. Sagan asked him, Is there a scientifically plausible way using general relativity to transport a person across the galaxy and bring them back with a massive time discrepancy like this without crushing them to death in a black hole?
And Thorne, rather than laughing him off, actually went to his chalkboard.
He took the question completely seriously. Thorne and his graduate students worked out the math, and in doing so, they completely revitalized the modern physics study of wormholes.
Oh, wow. A sci-fi novel pushed real physics forward.
It did. Thorne realized that a traversable wormhole, a tunnel through spacetime, could absolutely function as a time machine. It could create the exact scenario Sagan needed for Jodie Foster's character.
Okay, we need to unpack wormholes. How do you actually build a bridge through time? How do we bend the fabric?
The classic visual analogy for a wormhole is one you've probably seen in movies like Event Horizon or Stranger Things.
The pencil and paper thing?
Exactly. Imagine taking a flat piece of paper. That paper represents normal, flat space-time. If you want to get from a point on the far left edge of the paper to a point on the far right edge, you have to draw a long line across the whole page. That takes time. You are limited by the speed of light.
But if I fold the paper in half, so the left dot touches the right dot,
You can take a pencil and punch a hole straight through the two dots.
bypassing the whole page.
You have created a tunnel, a wormhole. You can instantly travel from one point in the universe to the other without having to cross the billions of light years of intervening space.
Because you went through a higher dimension?
Right. You bypass the speed limit not by going faster, but by taking a topological shortcut.
Okay, that makes sense. That is a shortcut through space. But how does Thorne turn that into a shortcut through time?
He combined the wormhole with the twin paradox.
Oh! Oh, wow. Okay, keep going.
Imagine we have the technology to create a stable, traversable wormhole. It has two ends, or mouths. Let's keep mouth A right here on Earth, locked in a laboratory. We take mouth B, we load it onto a hyper-advanced spaceship, and we send it out into deep space at nearly the speed of light.
Like Remus?
Exactly like Remus. So the ship carrying mouth B zooms around the galaxy for a while and then returns to Earth.
Okay.
Now, we know from the twin paradox that the ship and everything on it, including Mouth B, has experienced less time. Mouth B is aging slower than Mouth A.
Let's put numbers on this so I can really visualize it.
Sure.
Let's say we launch the ship in the year 2030. The ship flies around, comes back, and lands back on Earth. According to the calendars on Earth, the year is now 2040. 10 years have passed.
Right.
Mouth A has been sitting in the lab for 10 years.
But for the ship, because it was traveling at relativistic speeds, only 1 year has passed.
Yeah.
So Mouth B thinks it is the year 2031.
So I have these two wormhole mouths sitting right next to each other in the same laboratory, but they are out of sync.
They are internally separated by 9 years of time. They are connected through the higher dimensions of spacetime, and that tunnel is essentially a bridge between two different eras.
So if I am standing in the lab in the year 2040 and I step into Mouth A.
You will walk through the short tunnel, and you will step out of Mouth B.
What?
But because Mouth B is temporally synced to the year 2031, you will emerge into the laboratory in the year 2031.
My mind is blown.
You have traveled 9 years into the past. You have built a closed time-like curve. You have a functional time machine.
That sounds, honestly, that sounds way too easy.
Easy in theory, maybe.
Right. Obviously, building a near light-speed ship and harnessing the exotic matter required to prop open a wormhole is far beyond our engineering capabilities today. But the concept itself is so clean.
It is very elegant math.
There has to be a catch. Why aren't physicists universally accepting that time travel is just an engineering problem?
Because the catch is where general relativity violently collides with the other great pillar of modern physics, quantum mechanics.
Oh, boy.
And when these two theories meet, reality breaks down.
Explain that collision. Why do they hate each other?
Well, general relativity is the physics of the very large. It describes gravity, planets, stars, galaxies, and the smooth, curved fabric of spacetime.
Right.
Quantum mechanics, on the other hand, is the physics of the very small. It describes atoms, subatomic particles, probabilities, and the chaotic, jittery energy of the microscopic world.
So smooth versus jittery.
Exactly. When we try to describe a wormhole time machine, we have to use a mathematical framework called semi-classical gravity, which tries to awkwardly stitch these two theories together.
And it doesn't work well.
Quantum mechanics, quite frankly, utterly hates the idea of a time machine.
Why does the quantum realm care if I build a time machine? What does it do to stop the wormhole?
It comes down to something called vacuum fluctuations. In quantum mechanics, empty space is never truly empty.
Wait, what do you mean? Empty is empty.
Not at the quantum level. If you take a box, pump out all the air, block all the light, remove all the radiation, so it's a perfect, absolute vacuum, it is still not empty.
When it's in it.
At the quantum level, the space is boiling, is a frothing sea of virtual particles.
Virtual particles.
Tiny fluctuations of pure energy that pop into existence from nothing, borrow energy from the universe, and then annihilate each other instantly. It happens everywhere, constantly.
Okay, so the universe is fizzy at the microscopic level. What happens when that fizz gets near our time machine?
Imagine one of these quantum vacuum fluctuations, just a random pop of energy, occurs near mouth A of our wormhole in the year 2040.
Okay.
A tiny photon of light enters the wormhole. It travels through the wormhole and exits mouth B in the year 2031.
It has traveled 9 years into the past.
Now, that photon travels through normal space, just flying around the laboratory for 9 years.
I see where this is going.
Eventually, the year 2040 arrives again. The photon is still there, and it enters mouth A again. It travels back to 2031.
It's looping.
It loops infinitely. The exact same photon traverses the exact same region of space-time an infinite number of times.
That's a lot of energy.
And it's not just one photon. The calculation showed that as soon as the wormhole becomes a time machine, at the exact, precise fraction of a millisecond that the time loop is established, every single random vacuum fluctuation piles up on itself.
Oh my God.
The energy density spikes to infinity in an instant.
I have an analogy for this.
Yeah.
Anyone who has ever been on stage or in a recording studio knows exactly what this feels like.
Come on.
It's like putting a live microphone too close to a speaker.
Yes.
The microphone picks up the ambient noise in the room, sends it through the amplifier, and plays it out of the speaker. But because the microphone is too close, it immediately picks up the sound from the speaker.
And amplifies it again.
Right. It runs it through the amp again, louder, out the speaker, into the mic, louder. And within a fraction of a second, you get this deafening, screeching, high-pitched feedback loop that instantly builds up and blows out the amplifier.
That is a perfect, brilliant analogy. The universe creates a quantum feedback loop.
And it just blows out the amp.
The energy of the virtual particles amplifies infinitely, and that infinite spike of energy would instantly crush or vaporize the wormhole. The universe destroys the time machine before a single human could ever step foot inside it.
That is incredible. The universe defending itself.
This mathematical realization led Stephen Hawking to propose one of his most famous ideas, the chronology protection conjecture.
The Chronology Protection Agency. I always loved that Hawking had such a great, dry sense of humor.
He really did. He playfully suggested that the universe has a built-in chronology protection agency that makes the universe safe for historians.
I love that.
His conjecture states that the fundamental laws of physics will always conspire to prevent macroscopic time travel. The quantum feedback loop is the universe's riot police. It shuts the operation down.
But wait, I have to push back here. Is the case closed?
Well,
Does the math definitively prove that the feedback loop destroys the wormhole? Or is this just an educated guess because the math is incomplete?
that is the million-dollar question, and it raises a profound point about the limits of human knowledge right now.
Because we don't know everything.
Right. The calculations that show the energy density spiking to infinity rely on that awkward, stitched-together math semi-classical gravity. But semi-classical math breaks down entirely at what we call the Planck scale.
The Planck scale. That's the absolute smallest possible measurement in the universe, right?
Yeah.
It's like the pixel size of reality.
Exactly. When energy densities become extreme and distances become infinitesimally small, our current equations just spit out infinity. They stop making sense.
They just throw their hands up.
To truly know what happens at that exact moment of the feedback loop, we cannot use semi-classical gravity. We need a complete, unified theory of quantum gravity.
Which we don't have. Physicists have been chasing that for a century.
We have been. String theory, loop quantum gravity, we are still searching for the theory of everything that unites Einstein and quantum mechanics.
So Hawking could be wrong.
Precisely. And without a full working theory of quantum gravity, we cannot say for sure whether the universe definitively destroys the time machine.
It might survive.
Some physicists argue that quantum gravity might actually intervene at the last microsecond to cut off the infinity, stabilizing the wormhole and allowing the time loop to survive.
The door is heavily guarded, but it is not entirely locked.
Exactly.
Okay, let's play the what-if game. Let's assume, for the sake of argument, that quantum gravity does step in. The feedback loop doesn't destroy the wormhole. We successfully open a portal to the past.
Okay, let's assume that.
If the universe does allow these time loops to exist, we immediately run headfirst into a brick wall of logic.
Oh, yes, we do.
This is where the physics stops and the philosophy begins. This is where it gets really fun and really messy.
Paradoxes.
What actually happens if you walk through that wormhole and try to rewrite history?
If we allow closed time-like curves to exist, we must confront the paradoxes. They are the most famous obstacles to time travel, the fodder for every science fiction plot, and they come in several distinct, deeply troubling flavors.
Let's start with the big one, the grandfather of them all, the grandfather paradox.
Classic.
Imagine a time traveler. Let's call him Kurt. Kurt hates his family history. He builds a time machine, uses a CTC, and travels back in time several decades with a singular, violent mission.
To assassinate his grandfather.
Right, Adolf. Long before Adolf ever meets his grandmother, and therefore long before his father is ever conceived.
It is the ultimate test of causality.
Right. So Kurt steps out of his time machine in the past. He finds his young grandfather, Adolf. He pulls out a gun, aims, and pulls the trigger. Now, here is the problem. If Kurt succeeds in killing Adolf, then Adolf never has children.
Kurt's father is never born.
If Kurt's father is never born, Kurt is never born.
And if Kurt is never born, he never grows up, he never builds the time machine, he never travels back in time, and he never pulls the trigger.
Which logically means Adolf lives.
But if Adolf lives, he has a son who has a son named Kurt.
And Kurt grows up, hates his family, builds a time machine, travels back in time, and kills Adolf.
Which means he doesn't kill him.
Which means he does.
It's a logical short circuit. It literally breaks reality.
In philosophy, A cannot equal not A. An event cannot both happen and not happen simultaneously. It is fundamentally illogical.
Yes.
This is why most people, and honestly even most physicists for a long time, just threw their hands up and said, time travel to the past is impossible. The logic simply doesn't hold. End of story.
That is called a contradiction paradox. It's a direct violation of cause and effect. But there is another type of paradox that I find even more unsettling.
Oh, more unsettling than breaking reality.
I think so. It doesn't involve a contradiction. It doesn't break causality. Yet it is equally troubling to our understanding of the universe.
What's it called?
It's called the bootstrap paradox, also known as an ontological paradox or an underdetermination problem.
Okay, let's imagine Kurt takes a different approach. He doesn't want to kill anyone. He just wants to save himself some time.
Much friendlier.
So Kurt takes a book off his shelf, a very specific, highly technical textbook titled How to Build a Time Machine.
Convenient.
He uses his already built time machine to travel back 30 years. He finds his younger self, a struggling college student, and hands him the book.
Past Kurt takes the book.
Right. He drops out of college and dedicates his life to it. She reads the book, follows the complex instructions perfectly, and buys all the parts.
It takes him 30 years of hard work, but he finally finishes building the time machine in his garage.
He is now future Kurt. He dusts off his hands, walks over to the shelf, picks up the exact same physical copy of the book he was given 30 years ago, steps into the time machine, travels back 30 years, and hands it to his younger self.
Okay, I see the loop. The timeline is consistent.
Kurt exists, the machine is built, but here is the question that keeps me up at night. Who wrote the book?
Exactly. Who actually generated the knowledge?
The information inside the book, the equations, the blueprints, and for that matter, the physical ink and paper of the book itself, has no origin point.
It was never created by anyone. It was never invented. It just exists, eternally circulating in an infinite closed loop.
There's no contradiction here. Causality is technically maintained in a perfect circle.
But it violently violates our deep-seated understanding that things must have a cause, a beginning, a creator.
It's like the universe is pulling itself up by its own bootstraps, hence the name.
Precisely. But human psychology is messy. Free will is messy. It's easy to say, well, Kurt just changes his mind.
But it gets infinitely more complicated when we try to strip away human emotion and apply actual, cold, physical models to these paradoxes.
Let's talk about Polchinski's paradox.
Yes, let's. Who is Polchinski?
Joseph Polchinski was a brilliant theoretical physicist. In the early 1990s, he was looking at Kip Thorne's wormhole models, and he wanted to formulate a paradox that didn't rely on human choices.
No grandfathers, no books.
Just simple, Newtonian physics. Imagine a standard green felt billiard table. On this table, you have a mini wormhole.
A tiny wormhole on a pool table.
One mouth is the entrance on the right side of the table. The other mouth is the exit on the left side of the table. And the exit is temporally set to spit things out a few seconds in the past.
Okay, I have my pool cue. I am standing at the table. I take a solid 8-ball, and I roll it across the felt toward the entrance on the right.
Polchinski mathematically calculated that you could strike the billiard ball at a very specific angle and speed.
So if it goes in.
The ball rolls across the table, enters the wormhole on the right, travels back in time a few seconds, and exits the mouth on the left.
But because it exited in the past.
It rolls across the table and physically collides with its younger self before the younger self can even reach the wormhole entrance.
It knocked itself off course.
Yes. The older ball from the future strikes the younger ball in the present, deflecting its trajectory so that it completely misses the wormhole entrance.
But if it misses the entrance, it never enters the wormhole.
And if it never enters the wormhole, it can never travel back in time to strike itself.
It is a physical embodiment of the grandfather paradox, completely stripped of human psychology.
It is pure, relentless mechanics breaking down.
It's the universe refusing to compute. And there's one more paradox that I find fascinating, especially right now with the rise of AI, because it bridges quantum physics and computer science.
The easy knowledge paradox?
Yes. Let's explain this one.
This is a sophisticated variation of the bootstrap paradox, explored heavily by physicist David Deutsch.
Okay.
Imagine you have an extraordinarily complex math problem. In computer science, they call this an NP-complete problem.
These are problems that scale so poorly that a conventional supercomputer would take millions of years, or perhaps the lifespan of the universe, to brute force a solution.
Like trying to crack a massive encryption key or finding the absolute most efficient delivery route for 1 billion packages simultaneously, it's computationally nearly impossible.
Yes. So what does Deutsch do?
Imagine you hook your supercomputer up to a time machine with a closed time-like curve. You program a simple rule. The computer waits to receive a message from the future. The message contains the final, correctly calculated answer to the impossible math problem.
The computer receives the answer at, let's say, 12:00 p.m.
Right. It instantly outputs it to the printer for you to read. Then, at 12:01 p.m., it transmits that exact same answer back in time to itself at 12:00 p.m.
The computer never actually did the calculation.
Never.
It never crunched the numbers. It just received the answer for the future and forwarded it to the past.
It bypassed the fundamental limits of computational complexity entirely. It gained easy knowledge without doing any of the actual work.
Which deeply violates our understanding of epistemology.
Yeah.
The philosophy of knowledge.
Exactly. How is information generated in the universe? Does knowledge require work?
If a computer could just hand itself the works of Shakespeare, or the cure for cancer, or the grand unified theory of physics through a time loop,
The concept of discovery loses all meaning. The information just spontaneously exists for free.
So what does this all mean? We are at an impasse. We have Einstein and general relativity saying that time travel is a mathematical consequence of the universe.
We can build the wormhole on paper.
Right. But we have logic, causality, and epistemology screaming that it's impossible because it creates these reality-breaking paradoxes.
A universe where effects precede causes and knowledge is unearned is a universe of pure chaos.
This is exactly why people throw their hands up and say it's impossible.
But what if? What if physics has a built-in mechanism to prevent logic from breaking?
What if the universe is fundamentally smarter than we are and it autocorrects the timeline?
Now you're getting it.
This brings us to segment 5, and I want the listener to really lean in here because I think this is the most mind-bending, deeply philosophical, and arguably the most important section of our entire deep dive today.
It's a game changer.
This is the self-consistency theory. Let's dive in.
This theory was heavily championed by Russian physicist Igor Novikov in the 1980s, and it's known as the Novikov self-consistency principle.
Novikov. Okay, what did he say?
Novikov looked at the paradoxes, he looked at general relativity, and he proposed a radical but mathematically elegant solution, he said. If an event exists that would cause a paradox or any change to the past whatsoever, the probability of that event occurring is precisely 0.
0, meaning it is not just unlikely, it is physically impossible.
Yes. The principle asserts that there is only one timeline, one history. You cannot change the past because your actions in the past already happened.
They are already woven into the permanent fabric of history.
You aren't rewriting the script, you are just fulfilling your role in it.
Okay, let's apply this. I want to put Novikov's theory to the test. Let's go back to Kurt, who was standing in the past with a loaded gun pointed directly at his grandfather Adolf.
Okay.
What does Novikov say happens next?
Novikov says Kurt aims, he pulls the trigger, but so The gun jams. A mechanical failure.
Kurt brought a backup gun.
He pulls out the backup gun. He fires, but he slips on a banana peel or a wet spot on the floor, and the bullet misses.
Seriously?
Or he hits the target perfectly, but later discovers he hit the wrong person. Someone who merely looked exactly like his grandfather.
What if he hits his grandfather?
Or the bullet hits his actual grandfather in the shoulder. Adolf survives. He is rushed to the local hospital, and while recovering, he meets and falls in love with the young nurse who will eventually become Kurt's grandmother.
Wait, so whatever Kurt does, the universe physically prevents him from causing a paradox.
Absolutely.
In fact, you're saying his attempt to change the past might be the very catalyst that causes the past to happen exactly the way he remembers it.
Precisely. The timeline is inherently unbreakably self-consistent. The local laws of physics will always conspire to prevent a logical contradiction.
But wait, hold on. You're losing me. I understand how that works in a story. It's dramatic irony. But how does this apply to Polchinski's billiard ball? That wasn't human error. That was math. The ball is on a mathematically perfect trajectory to hit itself, right? How does the universe stop a physical object in motion without violating the laws of physics? The universe can't just magically make a cosmic banana peel appear on a billiard table to deflect the ball.
You are asking the exact right question, and this was the exact challenge taken up by Fernando Echeverria and Gunnar Klinkhammer.
Who were they?
They were two brilliant physics students at Caltech in the late 80s working under Kip Thorne. They analyzed Polchinski's billiard ball scenario using the strict laws of classical mechanics.
What did they find?
They wanted to see if they could find a mathematically valid solution that didn't violate the laws of motion but also didn't cause a paradox. And they found one. It's called the glancing blow resolution.
How does the glancing blow work? Break it down for me.
Let's rerun the pool table scenario. You roll the older ball toward the wormhole entrance.
It enters, travels back in time, and emerges in the past from the exit mouth.
But due to the complex gravity of the wormhole itself, it doesn't emerge on a trajectory to knock its younger self completely off the table.
So it misses.
Not completely. Instead, it emerges on a slightly altered trajectory. It rolls toward the younger ball, and it delivers a glancing blow.
A glancing blow.
Just a clip. Yes. The older ball from the future clips the younger ball in the present. It alters the younger ball's trajectory just enough so that the younger ball still enters the wormhole entrance.
But at a slightly different angle than you originally aimed.
Exactly.
All
And
right.
because it entered the wormhole at that specific altered angle, it travels back in time and emerges on the exact trajectory necessary to deliver that exact glancing blow to its younger self.
Whoa. The interference causes the conditions for the interference.
Exactly. Echeverria and Klinkhammer found that there wasn't just one solution. They found infinite families of self-consistent trajectories for the billiard ball.
That is wild. The universe didn't need magic to prevent the paradox.
It didn't need to break the laws of physics at all. The laws of physics naturally settled into a stable, consistent loop. The ball knocks itself exactly into the path required to knock itself into the path.
That is incredible. And this reminds me of the research done by physicists John Wheeler and Richard Feynman, and later formalized by Tim Maudlin.
Yes, the continuous functions.
They prove this kind of self-consistency mathematically. Let's talk about the camera and the negative.
Yeah.
Because when I read this thought experiment, my mind completely fractured.
It is a brilliant, abstract thought experiment designed to illustrate how continuous dynamics force a fixed point, a consistent solution.
Set the stage for us.
Imagine you have an old-school camera loaded with black and white film. You stand in front of a time machine. You plan to take a picture of whatever object comes out of the machine.
Okay.
You take the picture, you take the film into a dark room, and you develop it into a negative.
Right. And for anyone who hasn't used film, a negative inverts the colors. Whatever was pure white in real life shows up as pure black on the negative. Whatever was pure black in real life shows up as pure white. They flip.
Now, here is the setup for the paradox. You take that developed negative, you walk over to the time machine, and you send it back in time.
Okay.
You send it back so that the negative itself is the very object that comes out of the machine and the very object you take a picture of.
Wait, I see the paradox. Let's trace it. If the negative coming out of the machine is black, I take a picture of a black object.
Right.
I go to the dark room, I develop the film, and the black object flips to white. So I hold a white negative, I put the white negative into the machine, it goes back in time, but a black negative came out.
It's a contradiction. Black creates white, white creates black, it breaks.
It appears to be a perfect logical contradiction.
But Maudlin, relying on the mathematics of continuous functions, points out a flaw in the setup.
What's the flaw?
Film exposure is not binary. It isn't just pure black and pure white. A camera captures light continuously. There are infinite shades of gray in between pure black and pure white.
Okay, so it's a spectrum.
If you run the mathematics of a continuous function mapping onto itself, there is a theorem called the Brouwer fixed point theorem.
Which dictates what?
It dictates that there must be at least one fixed point, a point where the input perfectly equals the output.
So in this case?
In the case of the photographic film, there is a specific, uniform, perfectly balanced shade of gray that, when photographed and developed into a negative, inverts into the exact same uniform shade of gray.
Mind blown.
Yeah.
So if I try to set up this paradox, the universe won't let me have pure black or pure white. The system will naturally settle on that exact specific shade of gray.
Exactly. The picture taken is gray. The developed negative flips from gray to the exact same gray. It goes back in time and emerges as gray. Consistency is maintained mathematically.
The universe finds the fixed point.
There is another elegant mathematical proof using a dial to illustrate this.
Tell me.
Imagine a physical dial, like a volume knob, that can rotate in a full circle. You set up a rule. You plan to look at the dial coming out of the time machine. Whatever setting it shows, you will physically grab it, turn it exactly 90 degrees clockwise, and send it back in time.
Again, a paradox. If it comes out pointing at 12 o'clock, my rule says I turn it to 3 o'clock and send it back. But if I send it back at 3, it should emerge at 3. But it emerged at 12. Contradiction.
If you map all the possible initial states and final states of that rotation on a topological shape called a torus.
Stop right there. Explain it like I'm 5. What is a torus and why are we mapping time on it?
A torus is a 3D shape that looks exactly like a donut.
A donut, okay.
Imagine you are an ant walking on the surface of a donut. If you walk forward along the tube, you eventually loop around the whole donut and come back to where you started.
That represents moving forward in time through a closed loop.
Right. If you walk sideways around the thickness of the dough, you also loop back to where you started. That represents the rotation of the dial from 0 to 360 degrees. Okay, I have my ant on a donut.
Now, if you rigidly enforce an instant 90-degree teleportation, you might think you've broken the loop. But reality is continuous. You cannot instantly teleport the dial 90 degrees.
My hand has to physically grab the dial, and it takes time to rotate it?
Exactly. The dial exists in intermediate states between the moment it arrives and the moment it departs. If you mathematically draw the line of that dial's continuous existence on the surface of the donut, the topology of the shape proves that the line must intersect itself.
Really?
No matter what crazy, complicated rule you invent for turning the dial, the system will find a self-consistent, fixed-point trajectory where the action seamlessly aligns with the timeline.
That is wild. The math actively fights the paradox. This is exactly how time travel is portrayed in some of the smartest, most atmospheric science fiction we have.
Oh, definitely.
Think about the German TV show Dark, or the movie The Final Countdown, or hell, even Harry Potter and the Prisoner of Azkaban.
All great examples of closed loops.
Whenever characters try to stop a tragedy in the past, their very interference, their very presence, is the thing that causes the tragedy to unfold. The timeline is unbreakable. It's a closed loop.
It is aesthetically and mathematically pleasing. It removes the messy, reality-breaking contradictions from physics. But, and this is a massive but, an unbreakable timeline has terrifying implications for human existence.
Which brings us to the dark side of time travel. The 2 a.m. existential dread of segment 6. Let's talk about the philosophical cost of Novikov's theory. Because if Novikov is right, and the timeline is utterly self-consistent, what happens to free will?
It vanishes.
It's gone.
If Novikov's principle holds true, a time traveler has absolutely no free will in the past. Your actions are entirely predetermined by the history that has already been recorded in the future you came from.
Let me make this concrete. Say I build a time machine and I go back to June 28, 1914. I am standing in Sarajevo. I see Archduke Franz Ferdinand's car approaching.
A pivotal moment in history.
Right. I know his assassination sparks World War I, which leads to World War II, which lead to tens of millions of deaths. I have a loaded machine gun. I am standing 10 feet away from the assassin, Gavrilo Princip. I have the power to stop him. Are you telling me I cannot pull the trigger to save the Archduke?
You cannot. You will fail.
Even if I'm screaming at my brain to pull my finger?
Even then, the gun jams, you trip, you are struck by lightning, you will not change history.
That is maddening.
Now, some philosophers argue this destroys human agency. It reduces us to meat puppets acting out a script. But physicist J. Craig Wheeler has a fascinating counter-argument that I love.
What does Wheeler say?
He points out that physics already restricts your free will every single day.
How so?
You may use your absolute free will, sitting in this room, to decide that you want to fly by flapping your arms. You truly desire it, you will it to happen.
But gravity dictates that I cannot.
Exactly. You may use your free will to decide to walk through a solid concrete wall, but condensed matter physics dictates that you cannot.
The fundamental laws of the universe restrict your physical actions constantly.
Wheeler asks, why is the consistency restriction on a time traveler any different?
Oh, wow. So being unable to shoot the assassin isn't some magical, mystical loss of agency. It's just a physical law of the universe, exactly like gravity.
Yes.
The universe simply doesn't allow paradoxes, just like it doesn't allow me to walk through walls. My brain can want it, but the physics of reality will deny the action.
It is determinism enforced by geometry. But there is a secondary problem here. Something philosophers call the embarrassment of riches, or an underdetermination problem.
What does that mean?
We established that the universe guarantees that you will fail to kill your grandfather or save the Archduke, but the laws of classical physics don't dictate how you fail.
Right. You could be a jammed gun, a banana peel, a sudden gust of wind, a heart attack.
Exactly. There are an infinite number of self-consistent histories where you fail. If you try to shoot your grandfather, maybe a bird blocks the bullet. Maybe a microscopic quantum fluctuation deflects the firing pin.
So the universe doesn't dictate how it stops you, just that it will.
Classically, there is no way to calculate or determine which of these infinite failure modes the universe will select. It's an underdetermined system. The math is incomplete.
So how does the universe decide? Does it roll a dice? Does it pick the easiest path?
That is where quantum mechanics enters the picture again. David Deutsch, who we mentioned earlier with the computer paradox, proposed a quantum model for time travel to solve this exact problem.
And quantum mechanics is all about probabilities.
Right. In quantum mechanics, particles don't have definite fixed states until they are measured. They exist in a superposition of probabilities.
Like Schrödinger's cat. It's alive and dead at the same time, in a cloud of probability right up until you open the box and force the universe to decide.
Precisely. Deutsch argued that quantum systems in a time loop avoid paradoxes by settling into what are called mixed states.
Okay, I'm going to need another ELI 5 on this. What is a mixed state in a time loop?
Imagine a simple quantum switch. It can be in one of two states, UP or down-in. You program a time loop to create a deliberate paradox. Whatever state the switch is in when it exits the time machine, you have a robot arm immediately flip it to the opposite state and send it back.
So if it comes out UP, the robot flips it down and sends it back.
It's the grandfather paradox for a simple switch.
Yes, it demands a contradiction. UP becomes down, becomes UP.
But Deutsch's math shows that the quantum system resolves this contradiction by entering a mixed state. When the switch emerges from the time machine, it is not UP and it is not down.
Then what is it?
It is in a state of 50% probability of being UP and 50% probability of being down.
It literally becomes a coin flip.
Exactly. So you measure it. Let's say you open the box, you measure the switch, and the universe collapses the probability. The coin flip lands on UP.
Following your strict rule, your robot arm flips it to down and sends it back in time.
Wait, if it goes back down when it arrives in the past, it's down, but I measured it as UP. The paradox is back.
Oh, you're right. It looks like it.
But Deutsch says you have to look at it from a many worlds perspective. To make the math work, Deutsch implies a multiverse.
The multiverse. We're going there.
Yes. In half the universes in the multiverse, the switch emerges UP, you flip it down and send it back. In the other half of the universes, it emerges down in, you flip it UP and send it back.
So the timeline isn't a single rigid thread like Novikov thought.
No, it's a probabilistic blend of states that maintains mathematical consistency across the aggregate of the multiverse.
But Deutsch's theory has been challenged recently, hasn't it? Our sources include some incredible recent papers by physicist Barak Shoshani.
Yes, Shoshani argues for a different kind of multiple histories model.
How is his different from Deutsch?
Shoshani's work is brilliant, and it is a direct challenge to the idea that we were trapped in a single, unchangeable Novikov timeline, or even Deutsch's weird mixed-state loops.
So what does he propose?
Shoshani proposes that paradoxes are resolved by generating genuinely distinct, independent, multiple histories.
Break that down for me. How is that different from Deutsch's multiverse?
In Deutsch's model, the quantum states are mingling and transitioning between parallel worlds to maintain an overall statistical consistency. You never really change the past of your world. The math just balances out across all worlds like an accounting ledger.
And Shoshani?
Shoshani explores models using complex branching spacetimes where a time traveler physically, tangibly alters events, but in doing so, they diverge the timeline into a new, independent history.
So I go back in time, I aim at my grandfather, my gun does not jam, I successfully pull the trigger, he dies.
You successfully changed the past.
But I don't vanish into thin air like Marty McFly fading from a photograph. What happens to me?
You don't vanish. You just created a branch. You originated in History A, where your grandfather lived, had a family, and you were born.
Okay.
You traveled to the past, and at the moment you pulled the trigger, you created History B. In History B, your grandfather dies in that alleyway.
So I am never born natively into that new timeline.
You are never born natively into that timeline. But the you from History A continues to exist in History B as an interloper, an orphan of a deleted future.
This is exactly the Avengers, endgame rules of time travel. Changing the past doesn't change your future. It just creates an alternate reality, or like the movie Tenet, or the butterfly effect.
Essentially, yes. Shoshani's math suggests that the universe protects causality by allowing space-time to fracture.
Fracture.
The number of histories required to resolve a paradox might even be finite and cyclic. You might bounce between History A and History B in a loop, combining elements of multiple histories with Novikov's self-consistency, but you can never, ever return to the exact History A you left behind.
So as we wrap this deep dive up, we are left with two utterly terrifying options for how the universe works. Option 1. Novikov is right. We are trapped in a predetermined script where our choices are total illusions, and the universe will physically, violently force us to act out a history that is already written in stone.
And option 2. Shoshani is right, and every single action, every time travel event, fractures reality into infinite, inaccessible timelines, completely isolating us from the universe and the people we originally called home.
It is a profound existential crossroads.
Physics hasn't definitively ruled out time travel. In fact, general relativity seems to beg for it. But physics has completely redefined what time travel would actually look like.
We are either bound by the rigid, unbreakable laws of a single, self-consistent universe, or we are scattering ourselves across an infinite lonely tree of multiple histories.
Either way, time as we understand it is forever changed.
If you are listening to this, sitting in your room, listening to the clock tick, think about the choices you made today. If the future has already happened somewhere in the geometry of space-time, and history always remains flawlessly consistent, are you truly making choices in your life right now? Or are you just playing out a script that was written at the dawn of the universe?
The physics of closed time-like curves heavily implies that the distinction between past, present, and future might just be an illusion of our consciousness.
Maybe pop culture had it wrong the whole time. Maybe Marty McFly never had a chance. Maybe the timeline was never fragile at all. Maybe every choice you make, every mistake you regret, every moment of joy already happened exactly the way it was supposed to. And maybe humanity's greatest illusion is believing we're moving through time at all.